let's take a look at the first one of these problems, which is computing direction fields on surfaces. And again, what we're going to see here is that a problem which for many years looked like a hard combinatorial optimization problem turns out to be a nice simple quadratic energy where we can easily find the global minimum. So the first thing I should say maybe is, why do we care about direction fields on surfaces? And lately there's been a lot of interest in quadrilateral remeshing, but let's not forget that these things also show up all over the place in other applications. For instance, we might want to control the fur on an animal, or do non-photorealistic rendering, or control anisotropic shading, or all sorts of other things. And so today I'm not going to hone in on any one of these particular applications, but I'm going to develop some mathematical and computational foundations that can benefit all of them. The basic problem is we have a surface like this bunny, and we want to automatically find a nice direction field. So a direction field could mean a cross field, like you see here, or a line field, or just a good old-fashioned vector field. But in all of these cases, what I really care about is finding the optimal solution. Now, what do I mean by optimal? This could depend on the application that I'm working with. For instance, if I'm just designing fur on an animal, I might already have some notion of where the cowlicks or the singularities in this field should go, and I just want to find the smoothest solution everywhere else. And a few years ago, we showed that you can do this by just solving a single linear system, so that's something that's very, very fast. A more challenging problem, or something that sounds more challenging, is to automatically come up with this field. So the algorithm is going to figure out for us how many singularities there should be, where they should go, what type they are. And this sounds like a very hard combinatorial problem. So we have to make these discrete choices. But actually what we're going to see today is that, again, it turns out to be just a single matrix factorization. So something that's also very, very fast. Usually the way we formulate methods for computing fields on surfaces is with energy minimization. So we have some energy E that measures the smoothness of a field psi. Often this is something like the Dirichlet energy. So you imagine if I have a vertex, I have a vector at every vertex of my mesh, then I'm going to take the difference across the edge, square it, and add that up over the whole surface. But there are a few challenges we can run into here. One is that in most applications we don't care about the magnitude of these vectors, but just their direction. So we have sort of a unit norm constraint to deal with. Another is that we have to somehow encode this idea of identification. So for a cross field, for instance, we want to ignore rotations by 90 degrees. Over the years, people have formulated lots of different energies for solving this problem, but these energies really aren't so easy to minimize. One of the earliest ideas was to take the angle of the field and plug it into a trigonometric function like cosine. But the problem with cosine, of course, is it has lots of local minima we can get stuck in. So it's an extremely non-convex function. A sort of related idea is to work with integers modulo 2 pi over n. But the problem now is we have to solve for these integer jumps. So this becomes a hard combinatorial mixed integer problem. Again, a non-convex problem. And finally, the approach most closely related to what we'll do today is to use something called representation vectors. So instead of working with the angles themselves, we work with the cosine and the sine of the angle. But now you have, again, this hard non-convex constraint that says each vector has to have unit norm. And the reason I keep emphasizing the non-convexity of these formulations is that it means in general we can't hope to find the optimal solution. Not only that, but the method we use to find this approximate solution can be quite slow, so we might need some sort of fancy mixed integer solver to get an approximate answer. Another problem with these formulations, and one I think has really been overlooked, is that this Dirichlet energy we want to minimize really doesn't mean a whole lot for unit direction fields. So for instance, if I have this singularity, as I move towards the center, the Dirichlet energy shoots off to infinity. And so if you come to me and you say, what's the smoothest unit vector field on the surface, I'm going to tell you, I have no idea, because all of these solutions have infinite energy. So what do you mean by the smoothest? And at first this kind of sounds like an esoteric mathematical problem, but it actually turns out to be a serious problem in practice as well. For instance, if I have this nice mesh of a sphere and two candidate solutions, one very nice smooth solution going from the north to the south pole, and another with lots of different singularities, then as you might expect, the Dirichlet energy will tell me, okay, the thing on the left, that's smoother. But now let's suppose I refine the solution around the two poles. So now this spike in energy is much better resolved. And so if I plug this into my Dirichlet energy, it's going to tell me actually the thing on the right is smoother. And that's not at all what I wanted. So what are we going to do about this? From a theory side, we're going to introduce some new energies, which are well defined even for solutions with singularities. And most importantly, they're all convex and quadratic. So again, we can easily find the globally optimal solution. These energies are geometry aware, so they capture things like the tips of the ears on this bunny. And we can optionally align with things like principal curvatures. On the practical side, this boils down to just factoring a single sparse matrix using something that looks very much like the usual cotan-Laplace matrix. And what this means is we get an algorithm that's about 20 times faster than the state of the art in practice. Not only that, but we get solutions that are smoother than the state of the art. And when I say smoother here, I really mean smoother as measured by the traditional angle-based energy that everybody else is using. Okay. So the first question we have to answer here is, how do we represent n vector fields on surfaces? And typically we think of a tangent plane on a surface as a copy of the real plane R2, where every vector can be expressed as a linear combination of two bases. But we can also think about this in terms of the complex numbers, where every vector can be expressed as just a single complex coefficient times a single basis vector. Now, how do we deal with identifications? Again, with a cross field, we want to ignore rotations by 90 degrees. Well, if we remember that in the complex plane, a rotation can be represented as e to the I phi for some angle phi, then for any vector z, we can write all the rotated copies as e to the I 2k pi over n, right, these four vectors here. And if I raise any of these values to the nth power, then what I get is the same vector u, which I'll call my representation vector. And this is really the same as this representation vector that I talked about a minute ago, except that for the moment we aren't going to consider this unit norm constraint. On a surface, I can pick a basis direction at every point, and then I can express a vector field as a coefficient function relative to this basis. And a really critical thing to remember here is that when working with this function, it's only meaningful relative to that basis. So when we go and do something like take the difference between vectors at two different points of the surface, we first have to measure the angle made by the bases with a common geodesic. And then to go from one point to another, we can apply the corresponding rotation. Now, since this rotation only depends on the shape of the surface, it's a constant, and so we just end up with a nice quadratic expression for the difference between vectors at different points. If we want the difference between two n vectors, then, as I described, we just raise everything to the nth power, and we make a change of variables. We go from these coefficients z to our representation vectors u. And again, this thing on the left is just a constant, and so we end up with a nice quadratic energy that we can sum up over the entire domain. So far we've dealt with this issue of identifications, but we haven't done anything about this unit norm constraint. And so to figure that out, let's take a step back and look at things again in the smooth setting. So typically we write this Dirichlet energy as just the norm of the gradient squared. But if we break our field apart into two parts, a unit field, psi tilde, and a scale factor a, then it's not hard to show we can also write this energy as a sort of quadratic form involving the Laplace operator and the angular velocity, meaning how quickly this unit field rotates as we travel along the surface. And the main idea here is to now redefine the energy of a unit vector field as the minimum Dirichlet energy among all possible rescalings of that field. So now, for instance, at a singularity, the vectors are free to go to zero. Of course, we don't want the solution to go to zero everywhere, and so we're also going to ask that the whole solution have unit L2 norm. And at this point, some of you may recognize that what we're actually solving is an eigenvalue problem, a smallest eigenvalue problem, or what in physics is known as a time-independent Schrödinger equation, where now the angular velocity plays the role of the potential. So another way of saying this is the energy of a unit vector field is being defined as the ground state energy of a particle that wants to avoid this infinite energy at singularities. Okay? Now to get the globally optimal unit vector field, we're going to minimize this energy over all possible unit direction fields. And if we expand our definition here, what we realize is what we're really doing is we're minimizing the usual Dirichlet energy over all vector fields that have unit L2 norm. And so again, that turns into just a smallest eigenvalue problem. So we solve this smallest eigenvalue problem. Once we get the solution, we normalize those vectors at each point. And the key thing about this procedure is it's very, very fast. How do you solve a smallest eigenvalue problem? Well, you factor your matrix just once, and then you repeatedly apply back substitution to a random vector. So that's something that's very, very fast. And of course, this pointwise normalization costs next to nothing. Here's one example. We have this frog, and if we compute the smoothest crossfield on the frog, it's very smooth, and the singularities show up in very natural places, on the eyes and the toes, for instance. To get a little more control over the appearance of our field, we can break this Dirichlet energy up into two parts, something called the holomorphic and the anti-holomorphic part. And then we can define our smoothness energy as an interpolation between these different energies. What this means in practice is, for instance, on this triple torus, the holomorphic energy is going to give us a solution with a lot fewer singularities, but the Dirichlet energy is going to give us a solution with straighter integral curves, straighter field lines. And so we have this very natural trade-off between number of singularities and straightness of these curves. Here's a slightly more challenging problem, this horse. And if we compute the smoothest line field, again, the singularities show up in very natural places, the tips of the ears and the bottoms of the feet. But if we zoom into the legs, we see we don't quite get what we might expect. On 3 of these legs, the lines naturally follow, from top to bottom, and on this other leg, it spirals around. And so again, we might want a little more control. So what we're going to do here is introduce an additional alignment term, a linear term, that just measures how much our candidate solution lines up with a prescribed field phi. And so now, instead of an eigenvalue problem, what we get is just a single sparse linear system where the parameter lambda controls the amount of alignment, how significant that alignment term should be. Again, to get the final solution, we just apply a pointwise normalization, and so again, this overall procedure is very, very fast. So what directions might you want to align with? Well, one natural choice is the directions of principal curvature. So here's a classical example, the principal curvature network on an ellipsoid, and here's what we get using our method. And I'm not going to go into detail about just how we do that. They're all in the paper. But the key point here is that it's just a very simple closed form expression involving a local stencil. So we don't have to do any kind of filtering of curvatures or thresholding of curvatures or anything like that. If we go back to this horse example and we compute this curvature aligned field, then again we see the singularities end up in nice natural places on the ears and the feet. But if we zoom into the legs, we see now that all of the field lines follow the legs naturally, as you might expect. Here's another example showing the trade-off between smoothing and alignment, and you can see if we do no smoothing at all, we just get a bunch of noise. If we do too much smoothing, we miss out on these geometric features in the face, and somewhere in the middle we get a nice natural solution. And I should point out that this is really the one and only parameter in our algorithm. You get to control how much smoothing there is, nothing else. Okay, and finally, I want to roughly sketch out just how we discretize this problem so we can solve it numerically. And what we're going to get here is a nice new finite element basis that is useful for working with vector fields on surfaces. So the first question is, what does a tangent space look like at a vertex of our mesh? And one thing we could try to do is pick some vertex normal. But what we're going to do instead is just pick a reference direction, like we did in the smooth setting, and then think of any other vector as an angle relative to this reference direction. Now, on a discrete surface, the angles around a vertex don't add up to 2 pi as they do on a smooth surface. And so the first thing we're going to do is normalize all these angles by the angle sum so that they do add up to 2 pi. And what you can imagine has happened here is we've taken these flat Euclidean triangles, and now since their angle sums are no longer 180 degrees, you imagine they have some curvature omega. Now, if we imagine that this curvature is uniformly distributed over the triangle, then the curvature of any subtriangle is just proportional to its area. And that's the key observation we need in order to be able to transport a basis vector just at a vertex, one of our discrete basis vectors, to all the points on the interior of the triangle. And from there, we scale down the vectors by the usual piecewise linear hat function, and that gives us our bases psi. To build our mass matrix and our stiffness matrix, we just work out the appropriate inner products, and we have all sorts of details and code describing how to do that in the paper. The key point is that the final problems that we're solving involve just positive definite matrices, and the sparsity of these matrices just involves the one ring of each vertex. Okay, so let's see how this stacks up against existing methods. And here's one simple example where I compare against the state-of-the-art mixed integer algorithm, which is very popular. And what you see is it produces a very nice smooth field on this torus, but clearly it's gotten stuck in some kind of local minimum. There's no symmetry in this solution. Whereas if we compute the globally optimal solution, either using the Dirichlet energy or the holomorphic energy, we get something very natural. And again, you see we can trade off between the straightness of these field lines with the Dirichlet energy and the number of singularities with this holomorphic energy. Here's another example, a simple example of smoothed cube, and you can see again this mixed integer formulation fails to put the singularities on the vertices, whereas this globally optimal solution finds those natural geometric places. If we then ask both algorithms in this bottom row to align with principal curvatures, you get what you expect, but if you look closely, the energy of this globally optimal solution is still a bit smaller. And again, I'm measuring this energy using the energy defined in the mixed integer paper, not the energy in our paper. Here are a few more real-world examples, more complicated models. And what you find in general is that the solutions we get look largely like the mixed integer solutions, although every once in a while you see a singularity that ends up in a bit more of a natural place. In terms of computational cost, again, because we just have to solve this single or factor this single sparse matrix, what we get is something much faster. On average, we see that we can compute these solutions about 20 times faster than this mixed integer approach, and here I'm actually using their implementation of the mixed integer library. The method is very robust, so we can work with terrible meshes, or we can add a little noise or add a little smoothing, and largely you see that the singularities end up in the same places. Okay, so in conclusion, what we did here is introduced a nice automatic method for direction field generation that has provably optimal solutions. It's in practice about 20 times faster than the state of the art, and we're just using standard numerical linear algebra. So if you have some fancy GPU linear solver you want to use, you can go ahead and use that as well. From a theoretical side, we introduced some new energies that are well behaved at singularities. We can trade off between the straightness of the field and the number of singularities, and we can align with principal curvatures, adjusting that with just a single parameter. We also introduced a new finite element basis, which may be useful in the future for other problems involving direction fields on surfaces. Pretty soon now we'll put some code online that has some nice streamlined visualization and also lets you edit the optimal solution after the fact with a trivial connections method. So if you don't like the optimal thing, you have some artistic criteria, you can still change where the singularities go. And that's all I have to say. Thanks for your attention.
Okay, questions. Point out, as usual, we have the microphones in the center.
Hi, Mark McLaughlin, Disney Animation. When I looked at that horse example, you know, in the one example, the one leg was going wrong, but the direction was very nice around, you know, the torso of the animal. Is there a way then to, I guess, get it so that it's nice on the legs and on the torso?
Yeah, so this really comes down to what your definition of nice is, right? And it
Well,
sounds
I
like
mean,
you have a pretty good notion of what nice is. And so what I would say is, you know, instead of using these principal curvature directions, if you're at Disney, what you could do is have an artist paint in some sort of guidance field. And one thing that's nice about this approach is you don't have to paint that guidance field in everywhere. If you have some idea, oh, I really want it to strongly follow some direction only on the side of the horse, you can paint in some vectors with big magnitude there, and everywhere else, just set the magnitude to 0. It'll optimally find the optimally smooth solution in all those other places.
Okay, thanks.
Yep.
Let's do one more question, and I think we need to move on. Yes, go ahead.
Is your goal to reduce nonlinear problem to linear problem always?
I'm sorry, can you say this again?
Is your goal or objective
Yeah.
To reduce nonlinear problems to linear problems.
Yeah, that's my goal in life. If I could do that, I would die happy. Yeah. Linear problems are great.